Hi folks, this is a little video on gel electrophoresis, how we make gels and run gels in our lab. Gel electrophoresis is another way. It's very distinct from the nanodrop in the previous video, but it does something similar. It's a way to allow us to analyze a DNA sample. We can check the DNA for overall quantity, how much we have, and quality. What's the quality of the DNA? How good is it? How clean is it? Is it, in the case of plant genomic DNA, we can tell if it's degraded into little pieces or if it's kind of whole long pieces of chromosomal DNA. And so here we got some of the basic stuff we're going to need. So Agarose Gel Electrophoresis, this is Agarose. It's like a little white powder, looks like that. And so what Agarose is it's kind of like a polysaccharide material purified from seaweed. It's in a lot of common household items, I think like shampoos, soaps. It's also in ice cream. It's used as a thickening agent because it's going to form like a gelatin. It's not gelatin, which is animal-based. This is agarose. And so it's even used in some desserts to kind of create like that gelatin-like stuff. But we use it to create these little slabs of gel. We're going to make our gels in this little tray, casting tray, kind of like we're making a little mold of Jello. And the agarose is good for separating DNA based on size. Again, you can check out the stuff on Canvas for better explanations and videos and graphics on how exactly gel electrophoresis works. Here I'm going to primarily focus on how we make our gels, how we load our gels, how we run them, and how we visualize them over here under a UV light source, and then how we can kind of read the results. So I'm going to kind of start making this gel. First thing I'm going to do is just take this powder. I'm making a 1% agarose gel, and I'm making 25 mils. So that means I measured out 0.25 grams of agarose powder, 0.25 grams mixed in with 25 mils of this running buffer called TAE will give me a 1% agarose gel. So I'm just gonna mix that up. It looks kind of cloudy. You can see the powder in the liquid, but I'm gonna heat it up in the microwave next to boiling and kind of dissolve this powder into this liquid in the microwave. So we're gonna zap this in the microwave and I'll be back in a little bit. Okay, so the agarose and buffer mixture has come out of the microwave, and so as you can see now, it's no longer cloudy. It looks kind of clear, just like a clear liquid, like water, but it's kind of thick, a little bit gelatinous, and we don't want to wait too long because this is cooling and it'll form a gel. Right now it's still kind of liquidy. So before I pour it into the mold, I'm going to add a little bit of this dye called ethidium bromide. We add this to the gel because this is what's going to allow us to visualize our DNA. When the DNA encounters this ethidium bromide, the ethidium bromide stains it. It's a flat planar molecule that kind of gets in between the DNA ladder, the rungs of the ladder, if you will. And when under fluorescent light, this stuff will glow. So it's going to help us see the DNA by making it glow under the UV light over here. We'll see that in a little while. So now that this is all mixed up, ready to go, I'm going to pour it right in here in our Jello mold, if you will. There we go. So this is still hot and liquidy. It's going to take maybe 15-20 minutes to solidify. This is basically a tray. We've got a comb in here. The comb, I don't know if you can see that. I'm trying to focus. Comb has little teeth. Later, when I pull the comb out, it'll leave these little holes where I can load up the DNA samples into those holes, and then I'll put the gel in here, run electricity through the whole thing, and the DNA will migrate. Because DNA is negatively charged, it will migrate to the positive pole over here, and that's how we'll separate the DNA through the gel. We'll see that a little better in a second. So now we're just going to wait a little bit and let the gel solidify. Okay, so the gel has solidified. It looks like this. You can see it looks a lot cloudier blue as opposed to that clear liquid. So this is kind of a gel material now. It's solid. And I took out the comb. That's the comb I was talking about. You can see the little teeth. And when I removed the comb, it left these little holes in the gel, right? These little wells. They're called wells, and that's where I can load my DNA sample in and pass electricity through this whole gel, and the DNA will kind of migrate downwards from those wells, separate out by size. So now I'm going to put it in the gel tank. The gel has to be submerged in running buffer, and that's what's going to conduct the electricity. So I'm going to pour some running buffer into this gel tank. And then just kind of cover the whole gel. Okay, so everything should be submerged. That's what it looks like. Next, I'm going to load DNA samples into these little holes there. I can't really do that and film at the same time, so I'm gonna pause here, load up the gel, come back, show you what it looks like, hook it up to the power supply, and run the gel. Back in a few. Okay, so I just loaded the gel. You can see where I placed the DNA because it's kind of stained with this dark dye, or not stained, but I mixed it with this dark dye so I could see what I was doing. Otherwise, it's really hard to load these tiny little wells with DNA. So here are our DNA samples. I'm checking the same 2 DNA samples that we did in the nano drop in the previous video. And as you can see, it just looks like a little watery liquid. So I can't really see that very well, but if I mix it with something called loading dye, sorry, I have that over here. Whoops, empty, okay. So see this stuff? This is called loading dye. It's kind of a thick, syrupy solution that's also dark blue. And I can take a little bit of this stuff and mix it with a little bit of my DNA sample so that I can see what I'm doing and load the gel over here. So I've got 3 samples here total. On the first lane on the leftmost side, that little kind of greenish sample, that's called DNA ladder. That's going to be a prepared solution of mixed DNA, different sizes, that I can compare my samples to. The next 2 samples are the DNA samples, the plant DNA samples that we checked by nanodrop. I loaded about a total of 5 microliters. They were both at a concentration of about 40 nanograms per microliter. So I got about 200 nanograms of plant DNA for each sample loaded into this well. That should show up as a nice, obvious result. If I don't see something, then something went wrong. But I loaded a lot of DNA so I could really see it on the gel. And I've got the ladder on the left-hand side for comparison. I've got this all hooked up to a power supply. And so I'm gonna pass electricity. I should say that this is hooked up to the positive pole, and the top hooked up to the negative. Because remember, DNA is negatively charged. So if I pass electricity through this, I want this down here to be the positive so that the DNA migrates down the gel towards the positive pole. This is all set up, ready to go. I'm gonna hit run. It's gonna run for about 15 minutes at 170 volts. I don't know if you can see that. See the little bubbles coming up? That means the gel is running. There's a little wire down there at the bottom of the tank. Electricity is being passed through. And very quickly you'll see this blue dye start migrating down the gel. So we're gonna let it do its thing. We'll check in on it in a little bit. Okay, the gel is not done running. It's only been running for 5 minutes, but I wanted to check in real quick and just to kind of show you how everything's moving, right? So if you remember the first starting point, everything was in the well. You can see everything's kind of moved out of the well and is migrating down the gel. Now keep in mind that blue stuff you see, those blue dyes, and even that orange stuff on the bottom, that's not the DNA. That's just an indicator of roughly how far the gel has run. It's got to run a lot farther than that, but it gives us a visual cue of where we are. And when those blue dyes, especially the front one, that purple one, gets about halfway down, the gel will be ready to run. But just kind of wanted to show you what I meant, how everything's kind of migrating out of the well and down towards that positive pole. And in a little while, we'll take the gel out of the tank, throw it on the UV light, and that's when we'll actually be able to visualize and see the DNA and see how it looks. So we'll check back in when the gel is done running. Okay, so the gel is done running. I've taken it out of the tank and I've put it here on the UV light source. So it looks something like that. You can see how much farther the dyes have migrated down the gel. Now I'm gonna come over here real quick and hit the lights because it's better if it's nice and dark to easily see the glowing little bands of DNA. I'm gonna switch on this UV light and that's what it looks like. So there's the ladder. The smallest pieces of DNA run to the bottom. Larger pieces of DNA stay on top. You can think of the gel as like a 3-dimensional kind of meshwork or netting or like a webbing. And as electricity is dragging the DNA along through the gel, The smaller pieces are able to kind of snake their way through this obstacle course quicker, and the larger strands of DNA kind of get tangled and held up, and that's how this separates DNA based on size, really simply. And over here, you can kind of see the ladder. This is kind of a picture of the ladder, and you can see the smallest piece of DNA is 75 base pairs, all the way up to, I can't read that, like 20,000 base pairs or something. So that's what we're seeing here. And there's our genomic DNA. There's one sample, two sample. This sample looks like it had a lot of degradation, a lot of smearing. What we want to see is a nice prominent band at the top, and then some smearing is inevitable, as we can kind of see there. So what I mean by smearing is, imagine I ran a ladder where all the DNA is so every single size imaginable that instead of a ladder you see like a continuous smear. So this DNA sample, although the concentration was good, the gel is telling us that the DNA is degraded. Nanodrop couldn't tell us that, but the gel can. Here we're seeing intact DNA, nice high molecular weight band, because again, these should be long strands of chromosomal DNA. They should be very large, on the order of 20,000, 30,000, 40,000 base pairs. Some degradation is inevitable, but we're seeing nice high quality long pieces of DNA up top. So that's what that looks like. I should mention two things I didn't mention before. The ethidium bromide dye that we use, that orange stuff I added to the gel way in the beginning, that's a potent mutagen and potential carcinogen, so you want to be careful with it. Don't get on your skin, always wear gloves. This UV light is really strong. You're not supposed to expose yourself to it. I'm wearing a face shield that's protecting my face and eyes from this UV light so I don't get a sunburn. And I don't get a sunburn on my eyeballs, more importantly. Otherwise, this is what the gel looks like. Again, you can see the materials on canvas for much more examples of DNA gels and nanodrops and how to read them and how to interpret them and the principles behind it all. But I just wanted to show you what this looks like in the lab with this quick video. So I'll even kind of take a picture of this and post this, and we'll have this data for analysis in class and in group meetings. Okay, so I hope that was helpful, and we'll see you soon.